Hi, my name is Talia. I'm a staff member at Discovery, and I'm going to help you do your homework today. Okay, so there's this guy, big sports guy. His name is Tom. He really likes the Green Bay Packers, and he's a huge fan of Aaron Rodgers. So he's like, Aaron Rodgers makes 2.48 touchdowns per game on average, and that's his claim. He really thinks that's true. And that's right here, the claimed average, right? And then there's this other guy named Dave that also a big sports guy, but he likes the Bears instead. And he's like, I think you're making that up. I think you're wrong. I think that you're inflating Aaron Rodgers' statistics. So, translation, he thinks that the average number of touchdowns per game is actually lower than 2.48. So he goes on and he conducts a study. He takes 65 games, a sample of 65 games, all the ones that Aaron Rodgers had played, and he calculates the average number of touchdowns per game out of those 65 games. And his results are 2.015 average touchdowns per game. Or he averages 2.015 touchdowns per game. And he gets a standard deviation of 1.179. And instead of just looking at this and saying, oh, he got a lower result, that means it's lower, we actually have to perform a hypothesis test on this using z-scores and an alpha significance value to figure out, is this result really significant? Did we really prove to a reasonable degree that the average number of touchdowns is less? Or is this just a fluke in the data and Tom's claim is closer to the correct value? So we're going to go through 5 different steps of this question. It's a little annoying because you have to get all 5 right to get 100%, but a few of them are multiple choice, and once you really get them down, it's pretty quick. So we're going to go through it all. When it gets to the z-score stuff, I'm going to go a little bit faster. If you want a more lengthy explanation of everything I'm doing, you might want to check out the teacher salary video that goes into how to use z-scores and stuff for confidence intervals, and some of those same concepts can be applied here. But also, I'm not going to go too fast, so I think it'll be fine. All right. So the first question just asks, what kind of hypothesis test should we use? Because we have a lot of them. We have z-test and t-test. We have two-sided and one-sided. So the quick answer here is, this is a one-sided z-test. We know it's a z because our sample size is greater than 30. That's kind of a pretty good benchmark to know whether to use z or t. If it's less than 30, we use t distribution, but here it's 65, so z is good. And then when we're talking about one-sided versus two-sided, this is a one-sided test because this guy is just saying that he thinks that the average number of touchdowns is less, right? So that's only one side of the distribution. If it was two-sided, that's just saying, oh, I think it's different. So it can either be higher or lower, and then you're looking at two tails of the normal curve that's higher or lower. That's why it's two-sided. But in this case, we're just looking at it being less than a certain value. So that's just one tail, one-sided. So it's a one-sided z-test, and also it's one sample, obviously, because he only performed one sample when doing this. So the answer to the first part is a one-sided, one sample z-test. That one's pretty easy to figure out just by reading the question. Okay, part 2. This goes into our null and our alternative hypothesis. And this is what you need to do before you start any hypothesis test, is know what you're testing for. And in short, the null hypothesis is basically just like nothing significant happened. The original claim, we can't disprove it because our sample didn't end up producing any significant results. So null is like no change. And the original claim is that the average is 2.48. So we just say it's denoted by HO, null, mean equals 2.48, right? Because nothing really happened here. The alternative would be, okay, we got this lower result and it actually means something. So we can actually disprove this, and that'll eventually be determined by whether or not it falls within this alpha range. But we'll get into that more later. But basically all you need to know is that our alternative hypothesis will always disprove the original claim. So it's kind of like what you're searching for is the alternative hypothesis. So the HA is that the mean is less than 2.48 because that's what the test is trying to find. If it's actually less than 2.48, like the result got us. So let me just write that over here really quick so we can reference it later. HO mean equals 2.48. HA mean is actually less than 2.48, right? And again, I just want to stress that even though we got a 2.015 sample here, that doesn't automatically mean that the alternative is true, even though it is less than 2.48, because we have to determine if this is significant or not based on this level. So that's why we're still trying to prove it. All right, part 3, this is a little more mathy. We're computing the test statistic. So the test statistic is a z-score. Don't get confused by the word test statistic. It's more simple than it sounds. So the way to find the test statistic in this case is just assume for a second that the null hypothesis is true, right? The average really is 2.48. And we're just gonna base off of that, just pretend. So in the middle here, the average always goes in the middle, is 2.48. What's even the probability in the first place that we would get 2.015 from a random sample if the true average is 2.48? And if that probability is really small, then we have significance there. But first you have to calculate the actual z-score for what this sample average would be before you start calculating probabilities. So on this normal curve, it's centered at 2.48, right? Reiterating, we're assuming that this is the average just for the sake of the test. Where would 2.015 lie on that curve z-score wise? So let's say it's about here because it's pretty far lower. 2.015. These are, let's just say, our x values. Sorry for the interruption. I was just rewriting these numbers in what their more mathy terms, what the symbols are, so it's easier to reference them when we're doing our equations and our calculations. Okay, so that's what I was saying. Let's say these are our x values on the x scale, and then let's change it to standard normal, where the mean is just 0, and then this is the z-score based on standard normal distribution. So to do that, to find the z-score, z is always equal to the value minus the expected value over the standard error. Okay, so this expected value is just the mean that we're pretending is the real mean here. So 2.48, and then our value that we're testing is this 2.015 value. And then the standard error. One mistake that often happens here is that people just take this standard deviation that was found in the sample and put it here for standard error. But we have to change it a little bit first. Standard error is actually equal to s over square root of n. Yeah.
Mm-hmm.
What?
I can confirm.
You can confirm. Thank you. Let me just write SD so it's a little more clear. Standard error is the standard deviation over the square root of n, and we do this just so we ensure that this value better fits the true population of games instead of just the 65 that we drew. It's just kind of like a way to fix the estimate a little bit. And so in this case, we had 1.179 as the sample standard deviation, and we divide that by the square root of n, which was 65, and that'll give us around 0.146, but make sure to keep more decimals on this so that your rounding doesn't affect this final answer. Okay, so you have this, and you can finally put it on the denominator, 0.146, and your z-score for the average of 2.015 is negative 3.180. So you should already kind of have an idea of what's going to happen here. This is a very low z-score. there's going to be very little probability here in this tail. And so you might have some predictions about what's going to end up being the result of this test. But either way, this z-score is your test statistic. Just remember that. Test statistic, z-score. Test statistic, z-score. I'm bad at saying statistic. Kind of ironic. Anyway. Negative 3.180 will be your answer for the third part. Okay. The fourth part is finding your p-value. And that is just coming from this, the probability that you get your result or something more extreme if this is your mean. So, in other words, assuming that this is the true mean, that the true average is 2.48, what's the probability that we actually got 2.015 or less than 2.015? Because if it's really low, then we have a problem. So we're finding this area to the left of our negative 3.18 z-score. And here we can use Python functions. Norm CDF would be good here. Or on the exam, I think you might have to use a table. I don't really know. But basically, I did it with Norm CDF. So to find this area here, you just do norm.cdf and then 3.180, and that'll give you that area there. And it ends up being very small, 0.000736. So this is a very tiny p-value. So I'm going to write it over here, but then I'm going to explain that a little more. 0.000736. So one big issue that students have a lot is it's hard to understand exactly what a p-value is. It's kind of a big number, but basically I kind of said this before. It's the probability that you got your sample result or something more extreme, right? So this is our sample result. We're saying it's less than the 2.48, right? So less than our sample result would be more extreme in this case, because we're going more extreme in the direction of our null hypothesis, which is less. And that's because, say we got something that was maybe even lower, right? We want to cover all of these cases to where, like, we got this result, but we want to cover all of the cases where we got this result or something less, because then that would still match the significance of our results. So the probability that we got our result 2.015 or something even less than that is 0.000736. Okay. So the final part, now that we have all of our calculations, we have our p-value more specifically, what do we do with the null and alternative hypothesis? And the answer is all based on the level of significance that was given to us. So as long as our p-value is less than alpha, we know we have something significant, right? That's basically what this means. Is like, this tells us which p-values matter and which ones don't. Which p-values can reject the null and which ones can't. Anything less than alpha, those p-values can reject the null. And so that takes us to the answer for the last one. We know that it's very, very, very unlikely that we got this result if the actual mean is 2.48 as he claimed. So we can say, you know what, it's pretty much impossible. This is the real mean. Because if it was, this is the probability that we get our sample results, and that just doesn't make sense, right? So we know that the mean should probably be a good amount lower than this, the real mean, and it might be something closer to this. We don't know exactly what it is. We can't say for sure exactly what the mean is, because that's not the test we did. The test we did is this plausible or not? And we pretty much said, it's not plausible. So, in the cute little sentence that's at the end of this question, we will say that we reject the null because, what does it say? Sorry, there's like a lot of like words. Okay, yeah. So, in this case, it would be that we reject Tom's claim and conclude that Aaron Rodgers' average number of touchdowns per game has to be less than 2.48. Don't get tripped up by the equal signs. Again, we didn't prove that it is equal to 2.015. This is just the result from one study, right? So we can't really claim this as the true average. We don't know what it is. We just know that it's definitely less than this, or with an extremely high probability. So in short, I'm just going to write it in short terms. Reject Tom's claim, which in other words is the null hypothesis. His claim is the null hypothesis. And we say that HA has some plausibility. And mean is less than 2.48. That's the alternative. All right, so those are all 5 parts of this question, but they all kind of lead into one another. You need to know each one before you start the next one. So it's really not so bad. It's really just one big problem. And yeah, I hope it clears it up. There's a lot of questions like this, so gonna need a lot of practice.